Okay, so I start with the review from the previous class. I started with a very basic comparison between SL2C and SL2R. Pretty much, I found kind of one property that makes them differ from one another, namely that while here in GL2C, every matrix is a scalar multiple. Sorry, every matrix is a scalar multiple of a matrix with determinant 1. That's not the case in GL2R if I take the scalars only in the real numbers. Pretty much because if I try to, you see, when I apply the trick here, which is I take a matrix and I divide it by any of the 2 square roots of its determinant. The point is that here, that what goes inside the square root symbol may be negative. And so when I perform the trick that kind of represents any matrix here as a scalar multiple of a matrix of determinant 1, the scalar may be a non-real number, and so I may, modulo real scalars, I may fail to represent every matrix as a real multiple of a real matrix with determinant 1. So that's pretty much what I saw, that somehow, while here I have a canonical isomorphism, if I focus only on the real numbers, what I have is just a canonical inclusion. Okay, and then I went on to characterizing those 2 by 2 complex matrices of determinant 1 that preserve bijectively the upper half plane, characterize them precisely as those in SL2R. Right? And when I say preserving the upper half plane bijectively, I mean by means of diraction through Möbius transformations. Right? So for a 2 by 2 complex matrix of determinant 1, it is equivalent for it to preserve, for its Möbius transformation to preserve U bijectively, and for the matrix itself to lie in SL2R. Right? So, and that tells me that at least those Möbius transformations that preserve the upper half plane bijectively, somehow they don't look so weird, right? Kind of, they look, I would say, actually kind of very familiar or very tractable, at least, because they actually come from a group of matrices that over which I have a lot of control or intuition. Okay, and then somehow you see the point is that here in a way I am already thinking about one of the models of the hyperbolic plane that I'm going to encounter, or that I'm going to study, and that's kind of the main interest of this theorem, to be able to apply it later when I actually begin studying this model. So in the next section, what I do is, well, I pretty much what I have in mind is somehow that I already know another model of the hyperbolic plane, which is the Poincaré disk, the unit disk, and I want to perform to obtain a similar result, to characterize those Möbius transformations that preserve the disk, the Poincaré disk bijectively, as some concrete group. So that's somehow the overall aim or purpose of this section. And so what I do is I introduce a matrix, a group, as a matrix-Lie group, as the group of certain matrices of determinant 1 that preserve certain bilinear form. That's pretty much what I'm doing. And first, I compute the actual elements, how the actual elements of the group look like explicitly, like how the entries look like explicitly for all elements of the group. That's the first thing I do. And the second is that I notice all possible ways of sending the upper half plane onto the Poincaré disk bijectively. Right? So it all amounts to choosing triples of distinct points counterclockwise oriented and sending these three elements of R bar to such three. I pick one specific Möbius transformation sending one U bijectively to D, and then what I show is that this group that I just defined, namely SU11 here, and which I characterized as those kind of coming really from pairs of complex numbers that satisfy this funny equality with a minus instead of a plus, right? And then just copying, kind of transposing and copying with the conjugate. So proving that this group is actually conjugate to SL2R in SL2C. So it's really SL2R, but kind of disguised. That's the point. Well, so here's the proof. And you see, kind of the main point is that a matrix that conjugates them is precisely one of the matrices that help me to see that they are conjugate is actually this matrix whose Möbius transformation takes U bijectively to D. So somehow this actually and this equality actually somehow should tell me that SU11, you see, if this one is the group of matrices whose Möbius transformation preserve U bijectively, this one should be the group of matrices whose Möbius transformations preserve D bijectively. And that's the next statement. The proof is an exercise.